Okay, I'd like to start today's class. As I mentioned last week, we complete all the theory related to beam problems. Today, we will review the beam problems which could be very interesting and useful for you to understand, better understand the beam solutions, derivations, and how to solve it. So today we're going to have a relatively short course and just describing what kind of beam problems will be covered tomorrow. So again, I would like to review some beam problems, and tomorrow class we will go through all the solution in detail. First one, as this problem is already in your lecture note, we have two beams, and each one, the length is the L, and this, the length of the right-hand side is also L, but those two beams are supported together, so that once this beam deflect, this left-hand side beam will also deflect due to the load contact force transmit at the contact point. And force P is applied at a point L/4. So this is the problem. And now we want to solve how much each beam will deflect. As you can see that this beam will deflect like that. This beam, I will draw this one first. This beam will deflect like that, and there will be some contact point, and the right hand side, this one will deflect like that. So again, how much the deflection of each beam, and how much, once we solve the deflection, we can easily calculate the moment distributions by just second derivative of deflection. So obtaining deflection is the critical one, and then we can get a moment and a shear force and even the rotation angle. Anyhow, we consider this case into two beams. So this one as a V1 means the on the right hand side. So each one, let's say this is the point, and this one we call V1 is a function of the x, and this one is also another beam curve, and this one is the given as a function of a V2. So to solve the deflection V1 of the right hand side beam, we always have a governing equation EI V, actually V1 4 times derivative, and Q1x. This is a governing equation. In this case, Q1x is the distributed load, and so using the singularity function, we describe this concentrated load P since it's a minus, so minus P, and X minus L over 4, this is the where the load applied. And please be careful, the power is the -1. So this one is the a Q1X, and now boundary condition is that X equal 0, which means at that point the shear force is now shear force will be EI 3 times derivative, that's the shear force, and moment equal 0 and the left hand side, because there is just a simple support, even though this simple support point is moves the certain point, but this one will be a there will be no moment transmit. And here the F is actually we don't know yet, so we just consider F as the boundary condition. We just pretend to know this F, and this is the definition of the shear force. And moment equals 0. Again, there is no moment there, so moment equals 0. And here also moment equals 0. But again, there we applied the force on the and here, and another reaction force F is applied here. Again, we don't know this F, but we consider them as the known value, and then we describe the boundary condition. So this is one boundary condition and second boundary condition. And X equal L, in this case, X equal L is here, X equal L here. And I'm sorry, this is not correct. V1 equals 0 and V1 prime equal 0, since it's a clamped. Okay. Now, for V2 on the left-hand side, Gaboni equation is like that, and Q2 is the distributed load, but as you can see that there's no distributed load, so simply Q2 it will be the 0. And now boundary condition of this clamped one is that on the left-hand side, V2 equals 0 and V2 prime equals 0, and X equal L, and here is the X equal L, and here is the X equal 0. And X equal L, V, again, this is the force V, now is given as the force minus F, and this is the definition of there's a 3 times derivative EIV. So this is the boundary condition, and another boundary condition is moment equals 0. Okay, so this will complete all the problem statement, but to solve this F, F was the actually unknown. So to get this value, actually there is a geometric constraint that V1 is this one. V1 at this much deflection will be the same as this much deflection. So the V1 at X equal L, 0, will be the same as the V2 at X equal L. So from this we can have this F. And now, again, when we integrate this, there will be 4 integration constant, which will be obtained by using this 1, 2, 3, 4 boundary condition, and also this 4 integration points constant will be obtained from this boundary condition. Okay, so this is the very interesting beam problem, and second, another one beam problem where this is the relatively easy. Again, there is the force P applied, and there is on the left-hand side is a simple support, and here is the clamped, and certainly this is the statically indeterminate problem, and there is the simple support and clamped. So simple support, there will be a V equals 0, and V equals 0, and moment equals 0. Okay, that's a boundary condition. At x equals L, there will be a V equals 0 and V prime equals 0. Now, again, the Gabon equation is the same as usual. And this Qx, again, minus P, x minus A, is where the load is applied. So this is the Gabon equations. And two boundary condition x equals 0 and two condition x equal L is this one. So we just keep integrating. We can obtain C1, 2, 3, 4. Okay, this is the relatively simple problems. But one of the very interesting questions we need to answer is to find maximum moment. Okay, maximum moment means that when we apply this force P, where does the maximum moment occurs along this beam? In other words, let's say this A and B is the given. Let's say A is large, then this P will be located like that, and A is small and P located like that. So the failure moment, failure location will vary, certainly vary depending on the position of P, depending on the A. So it would be interesting and useful to find the maximum bending moment, which can be calculated from here. Of course, this C1 and C2 are calculated from this boundary, four boundary conditions. Okay, so this is the one second beam problem. And now another beam problem is that say we have a simple support. Let's say this is the length C here. And here we have a location A. A is the location from left-hand side to loading point. Now, we have a simple support on the left-hand side, and very interestingly, we have a simple support in the somewhere inside the beam, and then on the right-hand side we clamped. So how to solve this kind of problem? Well, as briefly mentioned last week, here simply we can, if we imagine the deflection curve will be like that, right? So here simply there will be a certain reaction force R. Let's say R. R is certainly unknown. We don't know how much the reaction force will occur there, and then this reaction force will be applied to a beam. But what we know is that V deflection at x equals C is simply 0 because of this simple support. From this condition, we can obtain R. So this second solution describe what I mentioned, but there could be another solution and procedures. We can consider them as a two beam and separate them, and then one beam is the simple support at both ends, and the other one can be considered as a one side simple support, the other one is the clamped. And then since those two beams are connected, we can consider that V1, okay, this one is the V1 and this one is the V2. On the left-hand side, and here the V1 should be V2 and V1 prime should be V2 prime, which means that sorry. V1, because this V1 equals 0 and Vt is also 0, but the moment will be the same because there will be some reaction moment and there is the two reaction moment. So momentum will be the same, right? And then whenever it deflect on the left hand side, this one slope and this slope will be the same. So how many boundary condition? 1, 2, 3, 4. There is a 2 and there is a 2. So totally 4 plus, actually there are 2 plus 4 plus 2, totally 8 boundary condition. So we, V1, we have a 4 integration constant, and V2, we will have a integration constant, totally 4. So the 4 integration constant will be solved using these 4 boundary condition. But as you can see, this is a relatively more complicated than second method. So I recommend you to use this second approach. And this approach, the distributed load P can be written using the singularity function like that, and F, I can say F here. So F is X minus C, where apply the load. And then we simply use again this deflection equals 0 and moment equals 0, right? And here the deflection equal at X equal L, deflection 0, and slope equals 0. So using that, we can solve it. Now, like to introduce 4 different beam problems, and I highly recommend you to think. I will just define the problem, and that's and this then I will complete today's class. But I want you to try to solve yourself for one day today, and then tomorrow in class we will solve them one by one. So I will just describe the problem. First one is the say we have a beam length L, and we have on the left hand side there is the simple support. On the right hand side also a simple support. Okay, this is the simple support location A, and total length is the L. So middle span is the L minus 2 times A. Of course, here and there will be just a free end. And from here, x equal 0 to x equal L, there is a uniform distributed load Q0. So you know what will be the carbon equation, right? And now there is the 2 simple support positions. And now question is that find A. Find A means this one, okay, this A, which would minimize the maximum bending moment. What does it mean? Well, if imagine that this A position is extremely on the left hand side like that, the bending moment will occur at the maximum at the center. But if this simple support goes into center, then the maximum moment will occur at the supporting point. So there should be some optimal A, or A which will minimize the maximum bending moment. Okay, so this will be very interesting problem, and we need to we will learn from this simple but very interesting problem. Okay, second one. Here actually there are certainly several ways to solve it. One simple way is that since it's a symmetric with respect to the center, right, and the left hand and right hand is the same, always the same. So we can consider this is we can just solve this only one side. Okay, we can solve it like that because at the center I'm sorry, not this one. Okay, not this problem. Actually, it's not just clamped. We, when we cover the boundary condition, we learn about the sliding boundary condition. Sliding, what does it mean? When it deflect like that, this one is always a slope. Slope is a 0, but there will be a freely deflect in vertical direction. So if we consider them, so I will draw again here. We can draw this one as the like that and like that, and there will be some distributed load like that. But the boundary condition wise, on the left hand side, there will be a sliding boundary condition. Okay, so this is the case we can consider. But anyhow, I would like you to think and imagine. To try to solve yourself, and we will discuss tomorrow in class. Okay. Now, second problem we want to cover is that the beam, two beams are connected, and one beam, the stiffness is EI1, and second is EI2. And again, there's a completely connected. On the left-hand side is a simple clamped. On the right-hand side is subject to end load P, vertical P load, and this will certainly deflect, right? Deflect like that. But the point is that here the bending stiffness EI1 and bending stiffness EI2, they are different and different lengths. Well, I will further, okay, just consider L1 and L2. Now find the maximum deflections, or the deflected curve. This deflected curve is a function of x. That's what we would like to solve. Okay. Again, please try to solve yourself, and let's discuss tomorrow. Now, third problem, very interesting problem, is the two beams are now again connected, but connected at the right angle, 90-degree connected, and the bending stiffness and lengths and bending stiffness and lengths are the same. But at point A, we apply the load P in horizontal direction, but this A point will move to here, A prime. So find a new position, A prime, which will be a new location of the point A. Okay, new position. New position means that how much we have to deflect, say delta x, how much vertically delta y. Why there will be some vertical deflection? Well, since we apply the P, this one will simply subject to bending moment like that. and then bending moment like that. So that's why, of course, the point is that this one, right angle, 90 degree, will remain. But this one is simply, we have a deflection in vertically. So, okay, this is the A point, okay. So this will be also a vertical deflection because of this deflection, okay. So this is the third problem. See, all kinds, we can think of all different types of beam problem. Now we should be able to solve any kinds of beam problem. Beam problem. Now, the last one is that similar to previous, but now we have two beams, but with separated. There is the initial gap, okay, initial gap. There is a space, okay. There was an initial gap between two beams. Now the upper beams are loaded by the force P, where the center. And this point A will deflect, certainly, but how much? Well, if P is the, I mean, when this beam deflect, this beam will deflect by the delta and then touch, and then this beam will deflect. So there is the two-step movement. Again, here, first move by delta and then touch, there will be another movement. So find the deflection at A. Okay, that's the last problem we can think of. Okay, again, as I mentioned, we covered the several interesting beam problem, and these four cases we will consider, we will discuss in class. Okay, sometimes we use the Gaboni equation to get the deflection, but sometimes we just use a beam moment and curvature relations. So there could be several different ways of solving, but please try to think yourself. You don't have to solve and submit a solution. That's not our intention. You would have a one day to think, okay? Think as much as you can, and then we will discuss, we will solve it tomorrow in class. Okay, that's what I would like to cover today, and then I hope to let's see tomorrow. Okay. Thank you. Bye.